Hi. Today, my team and I will discuss the impact of temperature and salinity on the electrical conductivity of water. Why study this relationship, you might ask? Well, in Colorado and many snowy states across the US, salts are deposited on roads to curb ice buildup and prevent unsafe driving conditions during winter months. These salts eventually run off into the same rivers, lakes, and streams that support surrounding residents with potable water. Monitoring water quality via chemical analysis in a lab is often expensive and time-consuming. Salinity, the amount of dissolved salts in water, is a crucial water quality indicator because high salt concentrations make water hazardous to consume and degrade surrounding ecosystems and infrastructure. By measuring temperature and conductivity, we can determine salinity, allowing us to evaluate water quality cost-effectively. So we designed an experiment to answer our big question. How do variations in temperature and salinity affect the electrical conductivity of water? We believe that as temperature and salinity increase, so too will the electrical conductivity of water, because increasing these quantities leads to faster moving and a greater quantity of ions.
Thank you for that introduction, Dustin. My name is Colin O'Rourke, and continuing on, we have our experimental setup. To get ourselves started, we first cover the interior of two opposite sides on the rectangular container with aluminum foil. We place the container on a hot plate, and a metal slab is placed in between them. The metal slab serves as a protective layer while still heating up the rectangular container, but as to not melt the rectangular container. Next, we pour deionized water to an approximate depth of half an inch, measure the length, width, length and width of the container, and depth of the water. We then add about a gram of salt to the deionized water and mix until dissolved. Connect the multimeter to aluminum foil and the temperature sensor to the DAC, and the DAC to the computer running our lab view. We then turn on the hot plate, and using our temperature sensor and multimeter, we record the temperature and resistance of the water every 10 seconds for 5 minutes, and then we allow the water to cool. Once that's done, we repeat for a salt content of 5 grams, 10 grams, and 20 grams. Continuing on, we have our experimental setup in real life. You can see there's our tub of water. We have our aluminum foil on opposite sides with red and black wires connecting to our multimeter on the ground. We then have our coil connected to our temperature sensor, which is sitting in the water just behind the edge of the tub. You can't see it, but it's in the water over there. That's connected to our DAC along with our multimeter. The DAC is connected off-screen to our lab view. With regards to our variables, our independent variables are temperature of water and salinity of water, and our dependent variable is electrical conductivity of the water. We have a sampling rate of 0.1 Hertz. Next, finally, we have our sensors, which, as talked about earlier, we have our temperature sensor, an Omega 88L75K, which goes from 0 to 300 degrees Celsius, which is this beauty right here. We then have our multimeter, a Keysight 34461A, a True Volt digital multimeter, this guy right here, and our DAC, National Instruments USB 9219 DAC, which is the same DAC that we used in Lab 3. This guy right here. And with the setup out of the way, I'd like to pass it on to my good friend and partner, James. Thank you.
Now, I'm going to go ahead and walk you guys through some of the theoretical equations we'll be using to analyze our data. First up is an equation that models the conductivity as a function of temperature. Here we can see that the conductivity at some temperature T is dependent on a reference conductivity and temperature, as well as a parameter alpha known as the temperature coefficient of conductivity. For seawater, the value of alpha is approximately 0.0185 inverse degrees Celsius. Our second equation models the conductivity as a function of salinity. Here we can see that the conductivity is directly proportional to salinity, with a constant of proportionality that we expect to be between 0.6 and 0.7 milligrams centimeters per liter microsiemens. This third equation is an equation we'll be using to convert our resistance measurements into conductivity measurements. It depends solely on the geometry of the container. Next up, we can see some of our data. Here we can see the temperature effects on conductivity. We can see that as temperature increases, the electrical conductivity appears to increase for all of our salinities. We fitted that first theoretical equation to each of our data groups and found values of alpha. Here we found that the average alpha is approximately 0.015 plus or minus 0.02 inverse degrees Celsius. We can see that alpha kind of stabilizes with our higher values of salinity, suggesting it is not temperature dependent. Next up, we have a plot of our electrical conductivity versus salinity for 3 different temperatures. We fitted our second theoretical equation to this data and found our parameter of K to be approximately 0.5 plus or minus 0.6 milligram centimeters per liter microsiemen. As you can see in the variability in K for each temperature range, we can see that K is likely temperature dependent. Next up, we have our two-way ANOVA results. First up, we have our salinity ANOVA. We can see that we get a p-value of approximately 8.3 times 10 to the negative 149, which for all intents and purposes is 0. With this, we can conclude that salinity has a notable effect on the electrical conductivity of water. We have a similar situation with our temperature, a much higher p-value but well below the threshold, and thus we can conclude that temperature has a notable effect on the conductivity of water. Finally, we can look at the interaction effect between salinity and temperature. Similarly, there's a strong interaction effect between temperature and salinity on the conductivity of water. The last result I'll be sharing with you are just a comparison to known conductivities. As we can see here, our measured conductivities are very similar to the theoretical conductivities for all of our values of salinity. We are within our uncertainty range for our upper 3 values of salinity. We are just outside of our uncertainty range for our lower value of salinity of 1.1. We'll discuss why this is in our error analysis. I'll now go ahead and turn it over to Owen.
Thank you, James. Now we'll move on to our more general analysis and our conclusion, starting with our notable trends. We saw that our conductivity increased by about 1.5% for every 1 degree Celsius increase in temperature. We also noticed that our conductivity is proportional to our salinity. So for example, doubling salinity would cause conductivity to double. This matches up with our governing equations, so it's quite encouraging. Now we did notice that our temperature parameter alpha was much lower for our aqueous, or slightly lower for our aqueous solution than for just straight seawater, which is what our data came from. This we're going to chalk up to differences between our much more pure saline solution versus the much more complex seawater. We also saw that our K parameter, which related conductivity to salinity, was likely temperature dependent, as at different temperatures, the slope of our salinity lines differed. Okay. For our error, we had a lot of difficulties in measurement here. Our biggest issue was that the resistances we were measuring were quite high, and multimeters, especially auto-ranging multimeters, have a lot of issues measuring those resistances or even auto-ranging into the general vicinity of them, so we did have to manually range them. If we were to do it again, we'd probably want to use a dedicated ohm meter, or because our circuit, due to the just scale of the water we were using, was likely nonlinear, we would want to use a more specialized instrument that accounted for any capacitance or inductance in our circuit. We also had issues where the hot plate did not evenly heat our water, and we didn't have anything stirring to make sure that the water was a uniform temperature throughout. If we were to do it again, we'd probably want to find some way to evenly heat the entire vessel, maybe a larger hot plate, or we would just want some stirring to help the convection process. And our last issue, and probably the easiest solved of the issues, is our plastic container was just not up to the task of being heated on a burner. So it did melt slightly. This may have introduced some plastic into the water, which may have affected our results, but this was really more of a logistical issue than an issue that affected our results. Next time we'd probably want to use something made of ceramic or Pyrex instead of plastic. Now for our conclusion, the data we found, while it didn't exactly match up, our parameters were a little different. It did support our original hypothesis, where increasing temperature and salinity both result in a mostly proportional increase to electrical conductivity. As in our hypothesis, our experiment showed that changes in salinity had a more pronounced effect on conductivity than changes in temperature. However, our alpha parameter did differ between seawater and our saline solution, so we'd want to do further testing to verify that data is good. We also found that K is potentially temperature dependent, and we would want to do further testing with more advanced equipment to confirm this. These are our references, and thank you for watching.